Okay, hello everyone. Today I'm going to talk about the service-oriented cloud computing architecture, which is a paper from the Wei-Tek, Tsai, Xin Sun, Janaka, Balasooriya, Department of Computer Science, and Arizona State University. And my name is Wei-Tek. I'm from computer science student of Tsai University. So today I'm going to talk about my presentation consists of outline would look like this. Abstract, it consists of abstract, introduction, survey on cloud computing and cloud computing architectures and issues with current clouds, and service-oriented cloud computing architecture, SOCCA in short, and initial prototype and experiments, and lastly it consists of conclusion. Okay. This paper gives an overview of a survey of current cloud computing architectures and discusses issues of current cloud computing implementations, and it also proposes a service-oriented cloud computing architecture, in short SOCCA, so that clouds can interoperate with each other. SOCCA proposes high-level designs to better support multi-tenancy, which I will explain in a short time. Clouds have appeared as a cloud computing infrastructure that delivers computing resources as a utility in dynamically scalable and virtualized manner. And advantages of cloud computing of our traditional computing is agility, lower entry cost, and device independency, location independency, and scalability. There are many cloud initiatives from IT giants such as Google's, Amazon, Microsoft, and IBM, and other startups. Survey of cloud computing. Cloud computing is built on top of modern data centers, and most of the current clouds are built on top of the modern data centers, and it provides these services like utilities, so the end users are billed at how much they used, and also it incorporates infrastructure as a service, platform as a service, and software as a service. In this picture shows a hierarchical view of cloud computing, and data centers provides the hardware the clouds run. This one is data centers, and the foundation of cloud computing is data centers, which provides hardware the clouds to run, and infrastructure as a service. In short, IaaS virtualizes computing power, storage, and network. And IaaS is built on top of data center layer. And it offers it as a provisioned service to consumers. Users can also scale up and down these computing resources and on demand dynamically. Popular examples of IaaS are Amazon's EC2, Google's Compute Engine, and Microsoft's Azure platform. Platform as a service. The second one is provides development platform to assist application design and development, testing and deployment, monitoring and hosting on the cloud. It usually requires no software download or installation and supports geographically distributed teams to work on projects collaboratively. And the examples of these layers are Google's App Engine, Microsoft's Azure, and MapReduce, and Amazon's S3 included. Software as a service. Software as a service is a software that is presented as a service on demand to the end users, usually in a browser. It saves users from the trouble of software deployment and maintenance. It automatically updates from the clouds and no additional licenses needed to be purchased. Examples of software as a service is Google Maps and Salesforce.com and Zoho's services included. Both academia and industry have been active on cloud computing research, and several cloud computing architectures have been proposed. IBM researchers proposed reservoir architecture to create a federation from multiple cloud providers, which acts as a global fabric of resources that can guarantee the required SLAs. The reservoir model explicitly addresses first, the limited scalability of a single provider cloud, and second, the lack of interoperability among cloud providers. In reservoir architecture, the computational resources are divided by reservoir site, which is shown here, and within the resource site are partitioned by virtualization layer into a virtual execution environment, VE in short. And service application breaks down into a set of software components or services running on VEs on the same or different VEs within a site or across from different sites. The next architecture is discussed in the paper is Janaka. It is customizable and extensible service-oriented runtime environment that enables developers to build .NET applications with the support of APIs and multiple programming models. Janaka is service-oriented, pure platform as a service cloud solution. And the third one is market-oriented cloud architecture. Research Raj Kumar and his colleagues explained market-oriented cloud architecture in detail used by Janaka and promotes cost-based resource allocation mechanisms that differentiate service requests based on their utility. The key component of this architecture is a service level agreement (SLA), resource allocator, which is shown here, and which consists of a service request examiner, and access control, virtual machine monitor, and request dispatcher. Based on the feedback from the virtual machine and service request monitors, the dispatcher routes the request from the users or brokers to the cloud resources that can fulfill their cost requirements. So there is issues with the current cloud implementations. First, one cloud provider, and effort and money spent on developing the application for a specific cloud platform, which makes it difficult to migrate the same application onto different cloud. Often to migration application, you may need to redevelop the application again. Second one is components are tightly coupled. The advantages of building or buying include a wider selection of components, flexibility to customize, and cheaper costs. However, current cloud implementations don't allow this kind of flexibility. Third, lack of SLA supports. Currently, SLA is an obstacle that prevents wide adoption for cloud computing. Multi-tenancy can support multiple client tenants simultaneously to achieve the goal of cost effectiveness. Currently, one has two types of multi-tenancy enablement approaches: virtualization, mediation, and sharing. To achieve the full potential of multi-tenancy, three issues remain to be solved. And the first one is to reduce the hardware, software, and management cost of each tenant. And second, to prevent the potential invalid access, conflict, and interference among tenants. And three, for the last, to support tenant-specific user interface, access, control, or process, or data, etc. And most of the clouds SaaS users, software as a service users, are limited with user interface choices because user interface composition frameworks have not been integrated with cloud computing, not that much. And and we are presenting software service-oriented cloud computing architecture. And service-oriented cloud computing architecture is attempting to bridge SOA architecture to the cloud computing architecture. SOA is used to create, organize, and reuse business. It's to create business. It's computing components. Cloud computing, on the other hand, is a set of technology that services a bigger, more flexible platform for enterprises to build their SOA solutions. There have been several initiatives at attempting bridging SOA and cloud computing. And in this figure, you can see SOCCA's layered architecture. SOCCA, Service-Oriented Cloud Computing Architecture. From the bottom, architecture consists of individual cloud platform, cloud provider layer, resembles the current cloud implementations, and cloud ontology mapping layer masks the difference among the different individual cloud providers and help migration of cloud application from one cloud to the other cloud. On top of it, cloud broker layer, which serves as agents between individual cloud providers and SOA layer. Finally, the SOA layer, which can be integrated with many SOA frameworks, but also many other artifacts, can be published and shared, such as workflow templates and collaboration template registry and test case. Individual cloud provider layer. This layer resembles the current cloud implementations, as I have said earlier. Each cloud provider builds its own data centers that power the cloud service it provides. Each cloud may have its own proprietary virtualization technology or utilize open source virtualization technology such as Eucalyptus. Similar to market-oriented cloud architecture, composed before sections. Within each individual cloud, there is a request dispatcher. Working with virtual machine monitor and service app governance to allocate the requests to the available resources. And cloud computing resources in SOCCA are componentized into independent services such as storage services, computing services, and communication services, with open standardized interface so they can be combined with services from other cloud providers to build cross-platform virtual computers on the clouds. In order to achieve maximum interoperability, uniform standards need to be implemented. For example, SQL is the de facto standard for RDBMS data management, and many database vendors have their own implementations. Cloud version of SQL needs to be defined, and so the data manipulation logic of application that works on one cloud can also work on the other clouds. Cloud providers might not conform to the standards rigidly. They might also have implemented extra features that are not included in the standards. Cloud ontology mapping layer exists to mask the differences among the different individual cloud providers, and it can help migration of cloud application from one cloud to another. Several important ontology stems are needed as follows. Storage ontology. It defines concepts and terms related to data manipulation and on the clouds, such as data update, insert, delete, and select, etc. Computing ontology. It defines the concept and terms related to distributed computing on the cloud, such as map, reduce, framework. Communication ontology. It defines the concepts and terms related to communication schema among the clouds, such as data encoding schema and message routing. The next layer is a cloud broker layer. Cloud brokers serve as the agents between individual cloud providers and SOA layer. Each major cloud service has an associated service broker type. Generally, cloud brokers need to fulfill the following tasks. Cloud provider information publishing. Individual cloud providers publish specifications which consist of basic info about cloud provider itself and its resource type, and etc. And pricing info to the cloud brokers. Ranking. Service can be ranked in several categories such as price, reliability, availability, and security. Ranking can be achieved through users voting or historical service governance records. Dynamic SLA negotiation. Cloud service brokers can help cloud users and help providers negotiate on SLA dynamically. The next one is the on-demand provision model. Accurate demand prediction and provision become critical for the successful of cloud computing, which reduces the waste of utility purchase and can therefore save money using utility computing. SOA layer. This layer fully takes advantage of existing research and infrastructure from traditional SOA. Many existing SOA frameworks such as CCSOA, CC-SOA, consumer-centric SOA, UC-SOA, which is user-centric SOA, and global software interface GSE, and user interface modeling composition SOA can be integrated into this layer. The figure shows possible SOA layer for SOCCA. Not only the services, but also many other artifacts can be published and shared, such as workflow template, collaboration templates, and test cases. Fundamental difference of the SOA layer of the SOCCA from traditional SOA is that the service providers no longer host the published services anymore. Instead, they publish the services in deployable packages, which can be easily replicated and redeployed to different cloud hosting environments. Multi-tenancy architecture. As shown in previous pictures of SOA layer, SOCCA allows three different main multi-tenancy patterns. Multi-application instance and single application instance have explained on papers that they have referenced. Within SOCCA, new multi-tenant pattern becomes possible, which are called single application instance and multiple service instance, SOIMCI. SOIMCI pattern. Workloads are often not distributed evenly among application components, and the performance of single application instance is limited by application components having lower throughput. Better scalability is not only benefit from SOIMCI pattern, easily customizable is another gain for this pattern. Suppose in the sample application, see here is the payment service. Different tenants might have a different payment method requirements such as credit card, PayPal, or check. The application runtime environment, which is not described in this paper, will direct users of each tenant to correct services instance according to tenant's individual configuration. In the case that future tenant has payment requirement that cannot be met by existing service instances, say money order, and according service instance can be easily plugged into the existing service instances group. Service package. In SOCCA, services are published as redeployable packages, namely service package. Service package contains following required or optional information files. Compiled code. If service providers optimize the performance of their service by utilizing some platform unique APIs and features, compiled code for each platform is needed. The source code. It is useful to help its users to understand the service better, and it also gives the freedom to its users to tweak the services to accommodate their specific requirement. The configuration file. The services might use external basic services, for example, computing intensive scientific service, which also uses a lot of storage, might deploy its computing logic on a cloud that provides high performance computing power, but use the cheaper storage service provided by another cloud. Resources files. Any resource files that the service depends on, such as images or documents, are included in this category. So, SOCCA applications. In SOCCA, application development in SOCCA is similar to development in customer-centric SOA. The figure shows typical application architecture in SOCCA. First, developers search if there is any workflow template that matches the requirement, which is composed of service stubs or specifications which specify the functionalities and interface of services. Later, service stub is bound with a service package. After that, depending on the cost requirements and the budget for the application, cloud brokers will negotiate with cloud providers on SLA and deploy the service package on one or the multiple clouds. So, initial prototype and experiment. They have demonstrated web applications that has one easy requirement when each user visits the web page, he or she will be greeted by a random message retrieved from the Moto database. First, they developed the application by using Google App Engine, and second, they created a web service that wraps the Azure SQL service that allows retrieving and restoring motos from the Moto database deployed on Azure. 3. They utilized the web service connector tool to generate Google App Engine compatible client code to access web service developed by Step 2. 4. They created a class which has the interface to GAE data store to manipulate the data on the cloud. 5. A code snippet shows that depending on the config file, the application will be connected with either GAE data store database or Azure SQL database. And figure shows that after changing config file, the Moto app is now connected with Azure SQL database. As you can see, the end of the result, it says Azure SQL Moto database extracted from Azure SQL Moto database, and on the other result it shows extracted from the GAE Moto database. So the prototype demonstrates that the service package deployed on the one cloud can be configured to collaborate with service from other clouds. However, it doesn't show that a service package can be redeployed on different cloud, and instances for same service can live on multiple clouds. This is due to that currently different clouds supports different language sets, and there is no powerful modeling language to support developments for multiple platforms. They are currently developing this feature using modeling language PSML. So, in this paper proposed a service-oriented cloud computing architecture that allows application to run on different clouds and interoperate with each other. The SOCCA is a 4-layered architecture that supports both SAW and cloud computing. And SOCCA also supports easy application migration from one cloud to another and service redeployment to different clouds by separating the roles of service logic provider and service hosting or cloud providers. It promotes an open platform on which open standards ontology are embraced. This paper also introduced related topics for future research, such as service demand prediction and SLA negotiation, and service request dispatching algorithms. More work will also be conducted to devise the ontology systems needed for working SOCCA, and the prototype